We're asked to solve 0.7 to the x is less than 5. I'm going to show you two ways to do this. The safe way is, but it takes a little bit longer, is to do log to base 10 of both sides. When you do this, the sign doesn't change, and that's going to be relevant for my second method. The reason being is that without going into loads of detail, log is an increasing function. It looks like this. So if 0.7 to the x is less than 5, then log of 0.7 to the x is also less than 5. We can bring the x down, and then we can divide through by log of 0.7. But we just have to be careful here. Log of 0.7 is actually going to be less than 1. The reason I know this is that log of 1 is 0, so anything less than that is going to be negative. Okay, if you don't see that, then no worries, we can just check with our calculator. So that's what I would advise you do. Just see, is it negative or not? And it is, which means I have to swap the sign around. Then I can put that in my calculator. You could even use log to base 8 or something like that, but 10 is just a good go-to. So minus 4.5123. Write it down to that accuracy and then round it to 3 significant figures. There we go. Now there is a quicker way. There's a little subtle aspect to it, but I'm going to talk about it because it's worth knowing about. We could in fact go back to our original equation and do log to base 0.7. The only thing is that you have to then swap the sign around as you take the logs. The reason for this is that the log graph doesn't look the same. It actually ends up kind of looking like that, just a reflection in the x-axis. So it's now a decreasing function. Okay, this is quite subtle. And then we can bring the x down and you just get x is greater than log base 0.75. And that's like that is our answer without having to do any division. If you put that in, we get exactly the same thing. So it's almost evidence of why we have to swap the sign around because we get the minus 4.51. We've already shown with one method it's going to be greater than. So it shows that when we take log basically to a base that's less than 1, it's absolutely fine, but in an inequality situation, you must swap the sign around. You'll get the same answer. So to be safe, do the top method, but if you want to speed things up a little bit or just, understand logs a little bit better, then this is worth being aware of. Let's take a look at part B. Just made space down here for it. We're given a curve, y equals 8 minus x cubed, and then a rectangle is inscribed between it and the axes. And we're asked to find the maximum area of this rectangle. So the width of the rectangle is going to be x because it can vary. At this point where it touches the curve can move around along here. Okay, some different positions. So of course I get like quite a thin rectangle here. I'd get a much longer rectangle here, but a smaller height. So we're trying to find where it hits its maximum. But let's first of all just write down the area. The height is then going to be the same as the y value on the curve. So it's going to be 8 minus x cubed. We can therefore write down the area as base times height, x times 8 minus x cubed. 8x minus x to the 4. Okay, so that is a function of x. As x varies, I'll get some different areas. Now what we want to do, therefore, is to find the maximum is find the stationary points. So let's differentiate. dA by dx is going to be 8 minus 4x to the 3. I'm using the fact here that when you differentiate x to the n, you basically bring the power down, reduce the power by 1. You can use first principles differentiation to prove that. And this is going to equal 0 for stationary points, which includes the maximum, but for now, we'll just say stationary points. That means 4x cubed is going to equal 8, x cubed is going to equal 2, x is going to be the cube root of 2. And here, a is going to be, I'm going to actually put it back into the top one, so it's going to be the cube root of 2 multiplied by 8 minus 2, which is going to give me 6 times the cube root of 2 for the area. It's fine to leave that exact. You might just want to write it down to some decimal places as well. In fact, they do in the answers. That's the main reason I say it. So 7.56. It feels like that's going to be the maximum because the minimum is just going to be kind of a 0, if we just make it really, really have a really, really short height. But we do need to prove it. So for this, we can use the second derivative, the d2a by dx squared, which will be minus 12x squared. Again, I've times by 3 on this term and lowered the power. The 8 has a gradient of 0, it just disappears. And this is definitely going to be negative. Let's just find out what it is, though. It's going to be negative because x is positive, and I'm just doing minus a positive number. But I think to be careful in this sort of situation, it's best to just work out what it is. So we've got the cube root of 2, remember, and then I'm squaring it. So minus 19.0 when x equals the cube root of 2, because we're substituting that particular value in. And this is less than 0. Therefore, it's a maximum. It's greater than 0, you get a minimum. The reason being, very briefly, is that essentially, although the gradient is positive here, and then 0 and then negative, it's all about how the gradient is changing now. And the gradient's actually decreasing, it's going down, because it was positive, then it becomes 0, then it becomes negative, it's decreasing in size. And that's what's happening here with the negative. That shows us that it's decreasing. The gradient's decreasing, so it must be a maximum. Whereas it's the opposite for a minimum, the gradient's actually increasing here. That's why the second derivative is going to be greater than 0 for a minimum. Right, so find the maximum area. I've done it. A is going to be 6 times the cube root of 2, or we've got a 7.56, and we've shown that it is a maximum. Well done.